All right, so let's get started. So as mentioned, this question looks exactly like last week's question, but if you look carefully, I changed up the values. So what you want to do is calculate the amount of energy to change this 1,500 grams of ice, which is now at minus 20 degrees, to steam at 100 degrees Celsius. Give it a shot and send your final answer on the chat. Good luck, and I'm giving you a 5 minutes head start on it before I start dropping hints and reminders. Right. So to start off the question, right, you always have to ask yourself, right, whether we're dealing with a specific heat capacity, meaning that there's no change in state, or we're dealing with what? Latent heat, where there is a change in state. Also, you will notice that the mass was given in grams, but all the values up here, like specific heat capacity and vaporization, latent heat, and everything is given in kilograms. So what you need to do is change this to kilograms, and I'm going to trust that everyone could divide by 1,000 to convert it to kilograms. For step one, I'll label it too. For step one, and I'll try to color code it, right? Let me stick to that. Everything in red will be specific heat capacity, meaning that there's no change in state. For the first part, it starts off at solid ice at minus 20 degrees, and it just warms up to still ice, which is still a solid, at 0 degrees Celsius. Remember, before ice can melt, it has to reach solid ice at 0 degrees Celsius, and only then it can actually change to liquid water. So to calculate the energy here, the energy for this section, the formula, sorry, I should put HE, that's for heat energy. I have to use this formula, the red formula. So the mass is 1.5. The specific heat capacity of ice, we're dealing with ice, is 2,100. And the change in temperature is 20 because it went from 20 to 0. And last week, I told you all to always assume the temperature change is positive. So do not put minus 20 here. Let's see what we get. 1.5 multiplied by 2,100 by 20. How much people got this for the first part? 63000 joules. For the first part, 63,000. Right, so people are on the right track. Giving you more time, don't worry. The second part, right now, it's at ice. Sorry, yes, it is at ice at 0 degrees. So it's a solid. Now, the ice has to change into liquid water. But when it now changes, that water will also be at 0 degrees. So clearly, there is a change in state from solid to liquid. And latent heat also assumes that there's no change in temperature. So this is definitely the blue formula. And we have to use this value here, the latent heat of, no, not vaporization. This would be fusion. Fusion means we're dealing with latent heat, and it's changing from a solid to a liquid, or a liquid to a solid, right? So we have to use this value here, the 334,000. So for the second step, the heat energy is mass, which is still 1.5 kilograms, and the latent heat value is 334,000. Right? Let's make sure I have that correct. Something is blocking my view. Yep, that's correct so far. So we just have to multiply that, and we should be okay, right? Latent heat of fusion. And I'm getting this. Of course, you can always let me know if you got this value, so I'll know you are on the right track. Right? 501,000. Great. So people are saying yes. To give you a little jump start for the second part, for the third part, sorry, We're going from liquid water, which is at 0, and we're trying to get it to boil, which is also liquid water at 100 degrees. So this section here will be what? Specific heat capacity, because there is a change in temperature, but no change in state. So that's the red formula. A lot of answers are coming up, which is good. So for the third section, like I mentioned, it's the red formula. So to calculate the amount of heat energy here, it's the mass, still 1.5, by the specific heat capacity of water. This is normal water, liquid water, and the change in temperature is clearly 100. 1.5 by 4,200 by 100, get a huge-ish value. Right, and I trust everyone got this value. I think this section was the easiest section. And the next section is going to definitely be a latent heat of vaporization, because it's changing from liquid to gas, which is, well, steam. So for the fourth section, heat energy is the mass, which is still 1.5, and the vaporization value, the one with the V, is 2.26 multiplied by 10 to the power 6, right? Sorry for the bad handwriting there. 1.5 multiplied by 2.26 to the power. I'm getting this huge value, 3,390,123, 3 million and something. So to get the total energy, well, common sense would say, hey, we need to add up all the values. So let's do that. Anybody wants to confirm their answer? I think I'm getting the answer most people got. 4, 5, 8, 4 with 3 zeros. 1, 2, 3 joules. This is your total energy. I think somebody, it's 4 things you have to add up. I think one person missed one of the things. Add up all 4, I guarantee you, and you will get this answer. Right? So if you got it out without my help, feel real good about yourself. Let's go. All right, so here's how this game works, right? You have to defeat a witch here, right? So you have to do 3 things. Now, it's going to get harder, right? The first one is supposed to be easiest round. What you're supposed to do, everyone choose a number between 1 and 100. Now, I already know the answers for this one. Any number between 1 and 100. So 1 and 100 is included. So like you could choose 55. All right, so, and then choose any letter in the alphabet. So you could probably choose M. And you choose, and they're showing you how somebody would play the game. And then choose one of the items here, only one. You can either choose the potion, the eyeball, the bat, or the witch's hat, right? So for example, so send your selection. So when you're sending your selections, my selection would be 55, M, and the bat. And what needs to happen is that the witch is going to pull things out of a cauldron. And if any of your items appear, you lose. So the aim is for none of your items to appear. Once one item appears, you lose. So send your selections, right? Take your time. Take a few seconds. Lucky. Right? Like I said, the game will get harder and harder. So this witch's name is Grimalkin. If anybody knows who Grimalkin is, we read the same books. All right. All right. So let's see what's going on here. The first cauldron is 33. Was anybody unlucky enough to choose 33 between 1 and 100? You gotta have real bad luck. If you chose 33, you are out. Anybody who is still in the game? Right, so okay, but I don't really expect anybody to get kicked out in the first rounds, right? You gotta have real bad luck. Next one. K. Was anybody unlucky enough to choose K? Somebody out? Keishan, you're out? What, Kristen, you're out? Lord, that's real bad luck. That's 1 out of 26. Yeah, 26 letters to choose from, and it's only one appeared. K. All right. Last one. What if you chose the eyeball? You're gone through. You're out. How much people were able to survive all 3 wrongs? Only if you survive all 3 wrongs, you win. If you lost, well, let me know also. All right. So if you won, you have 1 win for the day. So write 1. You're going to have 5 wrongs today. Let's see how much of the 5 you can win. Let's move on. All right, so just like last week, this question looks just like last week, but I changed the values. And this one, you will notice that the mass is given in grams, but your values like specific heat capacity and the latent heat of vaporization is also in grams. So you don't need to change anything. You could leave the mass as grams because all your values up here is also in grams. So they match up. Good luck with this one. I think this one is going to be a little bit easier than the one we just did. I will, send your answers as usual. So it going from solid to solid, no change in state. So that's going to be the red formula. So for this portion, the heat energy is the mass. The mass is 800. We can leave it as 800. Specific heat capacity of ice is 2.1, a nice small value. And the change in temperature is 18. We are leaving it as a positive value. Just multiplying it here. 800 multiplied by 2.1 multiplied by 18. For the first part, I'm getting 30,240 joules. Give me a minute before I work out the second portion. Now, the next part is going to be the blue formula because it's going from what? 0 to 0. No change in temperature, but it's going from solid to liquid. So there is a change in state. So it's the blue formula. So the amount of heat energy, right? Shane, I think the part 1 answer, I think it is, your part 1 answer doesn't match up to my answer. So check it back now. It's supposed to be 30,240. Right, so this one here, the mass is how much again? 800. And the latent heat, this is fusion, right? It's going to be 334. 800 by 334. Huge value here. 267,200 joules. And the last part, well, answers are coming up really, really fast. So I should just work out this last part. This last part is going to be specific heat capacity because they're going from liquid to liquid. No change in state, but there's a change in temperature of 100 degrees. So the mass is 800, 4.2 for the specific heat capacity of water, and the change in temperature is 100. 800 by 4.2 by 100. I'm getting this 336,000 joules. And you all know what to do now. You have to add up all 3 answers to get the total energy. And I'm getting this as my final answer. I'll write it in the middle here. 6, 3. All right, no problem, Shane. All right. This is my final answer in green here with a big green arrow next to it. All right, so if you got that, congrats. Even if you didn't, but you understand your mistake, still take it as a win. All right, so Jada, you found out your mistake. Good, good. All right, so this is the one with the sun, right? So what's happening here? The lake. Now you want to calculate the power of the sun. The aim is to find the power. So remember last week I said power is work over time, but work and energy is the same thing. So the work and heat energy is the same thing. But to calculate power, the time has to be in seconds. So that's what I mentioned last week. So see if we can flip back in your notes from last week and see if you could calculate the power of the sun, right? Don't fall, in case you don't know how much a ton is 1,000 kilograms. So 4 tons is really 4,000 kilograms. And you will notice all the values at the top of the screen are already given in kilograms. So that 4,000, you do not need to change it to anything. Use the 4,000. Good luck, and let's see if you get the final answer correct. So this here is clearly the red formula because there's no change in state. The lake was what? Liquid water, and it just heated up that liquid water to remain liquid. So to calculate the amount of heat energy using the red formula, the mass of the lake is 4,000 kilograms. The specific heat capacity of water is 4,200. And the change in temperature, to go from 15 to 38, if you minus 38 and 15, you're going to get 23 degrees Celsius. So that's the change in temperature. So I suspect you're going to get a really huge number here when you multiply these things. Right, crazy number, but let's write it. These are numbers you're going to get in the exam too. 3864 with how much zeros? Looking like 5 zeros. 1, 2, 3, 4, 5. Think I have it correct there? Right. So that's the amount of heat energy. So that's the top part because heat energy and work is basically the same thing. There's a slight difference, but for this formula, let's just assume it's the same. It's okay to assume it's the same. So to calculate power is work divided by time. So we have the top part. The time has to be in seconds. So you have to convert. So power just now is work over time. We have the work, but the time has to be in seconds. So it's 5 hours, and every hour has 3,600 seconds. So let's, what 5 by 3,600 is how much? You'll get 18,000 seconds here if you multiply 5 by 3,600. So you're just taking these two values and dividing it. This guy divided by 18,000. So let's do that. 3,864 with 5 zeros. 1, 2, 3, 4, 5 divided by 18,000. Well, you didn't get something too bad. You're getting decimals, but 21466.666666. So you can go to 2 decimal places to be safe, right? I always recommend that you go to at least 2 decimal places in the exam. And power is measured in watts, right? All right, so the game is going to get harder now. Same thing, but look at the new instructions. For the first, the crow is saying that you have to choose a number between 1 and 75 this time. So getting last time it was between 1 and 100. So now it's going to be easier to lose the game. 1 and 75 are included. Then send your chosen letter and then choose one of the tokens. Remember, you don't want any of your items to show up. The aim is to get none to show up. So send in your choices. I'm always interested in seeing what you guys choose. All right, let's go and see what you guys, what luck you guys have on a Sunday morning. So the witch shows up. This is Malka the witch, and she hopes to win the game. First cauldron. Two numbers appeared. So, well, the 100 doesn't count, right? So if you chose 62, you are out of the game, right? You got to be real bad lucky to choose 62. Next cauldron, M. Was anybody unlucky enough to choose M? If you did, you are out of the game. And the last cauldron, the hat. A few people lost because quite a few people chose the hat. Did anybody win? Let me know. Right, so a few people, I realized a few people survived. Somebody choose M. How unlucky. 1 out of 26. Right. Right. Great, great. There's plenty of winners. Even if you lost, you have you have another chance the next rounds. Let's move on. All right, so here we have a strange question, but super popular in the exam. Here's how this question, let me describe this question. Here, there's a very strange piece of metal. We don't know the specific heat capacity of the metal. We just don't know it. Different metals like iron, brass, aluminum, different metals have a different value of specific heat capacity. Let's use your imagination here. Let's say that you have a pot of water, right? The pot of water is close to room temperature. It's 27 degrees Celsius. You can see it on the screen here. The water is initially at 27 degrees Celsius, and it's about half a kilogram of water. What you are going to do is take a piece of metal, the strange metal, 800 grams of that strange metal, which is at 150 degrees. So it's warmer than the water. If you were to place the metal in the water, would the temperature of the water rise or drop? Well, I'm talking about water. So you place the hot piece of iron into the water. Will the temperature of the water rise or will it drop? Common sense will say it will rise. So the temperature of the water will go up. What do you think is going to happen to the temperature of the metal? When you place hot metal in water, will the temperature of the metal go up or will the temperature of the metal go down? Right, it will go down. So the metal, the temperature will go down, and for the water, the temperature will go up. And the two of them will meet a common point. Believe it or not, after a while, the metal and the water will reach what we call an equilibrium temperature. Both of them will meet at a common temperature. And that common temperature today, in today's question, is 55 degrees Celsius. Have you all ever, well, I mentioned this last term, right? The conservation of energy. The conservation of energy is this. The energy at the beginning of a question is equal to the energy after. In other words, energy cannot be created or destroyed. It's just converted from one form to a next form. And we could actually use that concept to figure out the specific heat capacity of this unknown metal. Now, do me a favor. Before I start off, I want you all to draw this diagram and take down the question and take down this. Energy lost is equal to energy gained. Just take down those three things, and I want to do this question for you, right? So we're doing this, well, I doing it, and you just following along. So let me know when you are ready. Now look at this, right? Energy lost, like let's write back this same thing here, is equal to energy gain. Who is losing energy here? Is the metal losing energy, or is it the water losing energy? In situations, right? One item has to be losing energy, and the other one is always gaining energy, always. But the energy at the beginning and the end will be equal to each other. Right. The metal is losing energy because the metal started off as hot, meaning it had plenty heat energy. But then it got cooler because it went from 150 to only 55. So it got cooler. When things are cooling down, it's losing energy. And of course, the water is gaining energy because its temperature is rising. So how much energy is lost by the metal? Well, we could come up with an expression for that using the red formula, because the metal is not changing state. The metal, if you focus on the metal alone, the metal started off as a solid and it still remains a solid. So let's calculate the heat energy lost by the metal. The mass of the metal, I think I have to convert it to kilograms, because why? All my values up here is in kilograms. So I'm just going to divide it by 1,000. We all know we will get what? 0.8. So we're going to take the 0.8 multiplied by the specific heat capacity of the metal. Now, we do not know the specific heat capacity of the metal. So we just put specific heat capacity and you put small m here. So this means specific heat capacity of the metal. We just do not know its value. In fact, that's the aim of the question. That's what we're trying to find. How much is the change in temperature? Anybody wants to help me with that? The change in temperature of the metal. We are only focusing on the metal right now. What's the change in temperature of the metal? I'm getting 95, right? Because when you minus the 150 and 55, I'm getting 95. All right, great. So this is the energy being lost by the metal, and it's giving it up to who? The water. So this, whatever energy it gave up, is going to be equal to the energy gained by the water. So let's find an expression for the water. Now the water, there's no change in state. It started off as water at 27 degrees Celsius, liquid water, and it only raised to what? 55. So it's still going to be liquid water. So it's the red formula. The mass of the water is 0.5 kilograms. I have it written here. The specific heat capacity of water is 4,200. And the change in temperature of the water is how much? The water was 27, then it went up to 55, the equilibrium temperature. In fact, everybody reached 55 degrees. So what's the change in temperature of the water? Well, 55 minus 27, I can't do that in my head, so I have to put, right, so it's going to be 28. You all are correct. Now, Jordan, I think it's 28. Check it back now. Right, it's 28. So look at this, guys. We have a maths equation to solve, right? All you are trying to do is solve for this. So, and we can multiply the 0.8 and 95. Let's use our math skills. 0.8 multiplied by 95 is 76. And don't forget the specific heat capacity of the metal. And this is equal to these three guys when they get multiplied. 0.5 by 4,200 by 28 is this. 58800. You all can more than use your math skills to solve for this. This 76 is a multiply. Throw him across, you will get what? A divide. And once you divide it, you finish. Right? Make sure I put the correct units, sir. Specific heat capacity is measured in joules per kilogram degrees Celsius. So divide these two values and put it here, round it off to 2 decimal places as best as you can, right? And answers are just popping up on the screen, right? Great. Make sure you see something like this, 773.68. I put W here by mistake, right? But it's supposed to be M, right? Specific heat capacity of the metal. Let's move on. All right, so after that horrible question, right? Not that horrible. I think it was doable. You all know what to do here, but this time it has changed. You have to choose a number between 1 and 50. You notice the gap is getting smaller. 1 and 50 is included, right? Then choose a letter of the alphabet, and you all know what to do. Choose one of the tokens, only one. The potion, the eyeball, the bat, or the hat. This one I actually cannot remember the answer for, so I will play with you all. I am going to choose, I'm going to go smack in the middle. I'll choose 25, R, and I'm going to go with the potion. And I genuinely cannot remember the answer for this one. So I'm taking a chance just like you guys. 25, R, and potion for me. All right, let's see how lucky you guys are. Let's see how lucky I am. All right, so this witch name is Susie. First cauldron. 5, but I'm still in the game. Next cauldron. 2 letters, R or I'm out, because I chose R. So if you have R or Y, you are out of the game. Last cauldron. The hat. Did anybody survive all 3 rounds? Did anybody win? But I lost, so whatever. All right. Plenty winners. I think the hat killed a lot of people. They thought the hat would not have repeated. I thought the hat would not have repeated either. Right, so Salamata, you won twice. Jordan. One person finally won. All right, let's move on, guys. You have 2 more rounds. Don't worry, 2 more rounds to get your luck in place. All right, so here we have a strange question. Well, I like to make I like this question. It's about a comet that's about to hit the Earth, right? So what's going to happen in this question here? The comet, it's not a large comet. It's only 5 kilograms, right? But it's really, really hot. It's 2000 degrees Celsius. And it crashes into a lake, an 8-ton lake at -5 degrees. Now, this question is going to be different. Let me explain why. If something starts off at -5 degrees, that means initially it was ice. And then everything cooled down to 11 degrees Celsius. So that means the comet and the lake reached 11 degrees Celsius. 11 degrees Celsius is liquid water. So here's what. When the comet crashes into the lake, the first thing that has to happen, the ice has to cool down to 0 degrees. And then the ice has to melt from ice to water at 0 degrees. Then the water has to heat up to 11 degrees. It's a long question, right? But we're going to work this one out together. I want you all to write out the question. If you can draw a nice little diagram here, take down the question and let me know when you are ready. Remember, energy lost is equal to energy gain. The comet is going to be losing energy because the initial temperature of the comet was 2000 degrees Celsius. And then after it crashed in, everything reached 11. So the comet went from 2000 being very, very hot to only a mere 11 degrees Celsius. So let's calculate the energy lost. Now, remember, the comet starts off as a solid, and of course, when it crashes into the ice, we have to assume it remains solid. So it goes from solid to solid, no change in state. So that's the red formula. The mass of the comet is 5 kilograms. We do not know the specific heat capacity of the comet. So I'll put SHC in a small c here. That means comet. And what's the change in temperature of the comet? Anybody want to help me out there? What's the change of temperature of the comet? It's a huge number. It's a huge number. It's a minusing game. Number it started off at 2000 and then it went to 11. So it's just a minus 2011. It's a strange value, but 1989, right? 1989 degrees Celsius. So let's multiply these three things now, and that would be the energy lost by the comet. So it's 5 by 1989. You will get 9945 multiplied by the specific heat capacity of the comet. Remember, we just multiply these two, and we do not know the specific heat capacity of the comet. That's the aim of the question. So I'll put in a little line here. The 1989 came from minusing the 2011. That's the change in temperature of the comet. 2000 minus 11. Right. So let's calculate the energy gain. Let me get a different color here. I'll use blue, right? Now, who is gaining the energy? The lake, because the comet is giving up its heat, right? Okay, so how we got the 9945? We just multiply 5 on 1989. 5 multiplied by 1989 will give you 9945. And then you have to put back this here. Right? It comes like if you have 5 multiplied by x multiplied by 2. You can multiply these two on the ends. 5 by 2 is 10. And then you put back what? The x. The x comes like the specific heat capacity of the comet. All right, so let's move on, right? The energy gain. Now let's break this up into pieces. Initially, the lake was ice at minus 5 degrees Celsius. I'm gonna write that a little better. So you have ice at minus 5 degrees Celsius. Then it had to change to what? Ice at 0 degrees Celsius. Remember, the ice has to warm up first. Then the ice changed into what? Water at 0 degrees Celsius. And then finally, the water changed to 11 degrees Celsius. The water had to warm up after. Do we all understand this flow chart here? Because the lake was ice at minus 5 degrees Celsius. Then it went to ice at 0 degrees Celsius. It has to warm up. And once it had ice at 0 degrees Celsius, then it could use latent heat to change the water also at 0 degrees Celsius. Then once we have liquid water, then that liquid water could change to what? 11 degrees Celsius. So you have to calculate 3 things for me. 1, 2, 3. And when you calculate all three, add up all three, and that will be the energy gained. Then we can make an equation. Then we can say energy lost is equal to the total energy gained. So good luck. I'll give you 2 minutes. The first part of the calculation would be the red formula, the specific heat capacity, because it's remaining as solid ice, but there's a change in temperature. So the mass of the ice, normally, it's 8 tons. So that's 8,000 kilograms. So it's 8,000, sorry for the small writing there, by the specific heat capacity, which is 2,100 of ice, and the change in temperature is just 5, because it went from -5 to 0. So it's 8,000 by 2,100 by 5. Oh, some huge values here. 84 with 1, 2, 6 zeros. 1, 2, 3, 4, 5, 6. How much people got the first part correct? Let's do this in steps. Great. So people are agreeing with it. Right. If you got it wrong, well, all the working is there. Sometimes under stress, you just type it. You have it correcting on paper, but you're typing the wrong thing on your calculator. Right. For the second part, it went from ice at 0 degrees Celsius to water. So there's a change in state here, but no change in temperature. Blue formula. The mass is still 8,000, and the latent heat of fusion of water to ice or ice to water, right? 3 that's now 34000, right? Right, Salamatu, the change in temperature is 5, right? It went from -5 to 0. That's 5, not 6, all right? So check it back. So 8,000, that's our 8,000 by 334,123. Oof, huge value. Oh Lord, sorry to terrorize you over these huge values. 2,672 with 6 zeros. 1, 2, 3, 4, 5, 6. Sorry for this bent here. How much people got that? Some calculators would put it in standard form. That is same thing as what? 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 2.672 multiplied by 10 to the power 9. Right? So some calculators would have put it like this. Right? And the last part now, the last part is going to be a red part. It went from water, it's finally water at 0 degrees because the ice now melt. And it's going to change to water, which is also liquid at 11 degrees. So that's what? The red formula. The mass is still 8,000. Specific heat capacity of water is 4,200. I run out of space here. And then you have to multiply it by 11 because the change in temperature is 11 because it went from 0 to 11. So 8,000 by 4,200 by 11. Huge value again. Apologies. 3,696. But this time we get 5 zeros. 1, 2, 3, 4, 5. Right. So based on the answers, I'm seeing this. A lot of people did have it correct. To get the total energy, we add up all the answers. So let's add up all these answers. I'm getting this. 3, 1, 2, 5, 6 with 5 zeros. 1, 2, 3, 4, 5. Or some of you will have it like this. I'm going to put it on top here. 3.1256 multiplied by 10 to the power 9. Both are the same exact thing. Right? So that's the energy gained. by the leak. Look for your errors. I give everybody a few seconds, right? Comment. Remember, energy lost is equal to energy gain. So if this is the energy gain and this is the energy lost, and we can put both things equal to each other, 9945 multiplied by the specific heat capacity of the comet. We need to solve for the specific heat capacity of the comet. So this here is a multiply, throw it across, and you get what? A divide. When you divide it, your answer will be in what? Joules per kilogram degrees Celsius, because that's the unit of specific heat capacity. Divide it and let me know what you get. Try your best to round off the answer to 2 decimal places. This is what I am seeing. I hope I have it correct. You all can let me know. 314,288.59. It'll be 59 if you round off properly, because the 2 decimal places 5 or more. That is what I am getting. Right, so that's my final answer. Well, after that crazy question, I think you'll deserve one. Well, you have 2 more chances. All right, so this one I cannot remember either, so I will play with you all. I'm going to choose from numbers between 1 and 25, 1 and 25 included. Yeah, gonna go with 10, letter of the alphabet, T. Now, how today is Sunday, I'll choose S. Which one here? I'm feeling lucky with the potion. Right, so for me, it's going to be 10S on the potion. 10S on the potion. All right, so let's have a look. All right, so it's Susie again. Let's go. First cauldron, 18. Well, I'm still living because I chose 10. I hope, I suspect a couple people lost already, because I did see a couple 18s pop up. All right, next one. Oh, any of those letters, B, E, or T, you are out of the game. 3 letters came out of the cauldron, right? Quite unlucky. Last cauldron. 2 things came out, or I lost, because once you pick the potion or the bat, you're going to lose. I lost. I got through everything except the last step. Keishan, you won. Bridget, you won. Alia, you lost. Guida, you lost. Jason, you win. All right, Abby, you survived. Spring, this is your first lose. All right, so congrats to those who lost. I mean, sorry, hear me. Congrats to those who won. Sorry. Let's move on. All right, so for the rest of class, you have no more calculations. It's just definitions now. Right, let me explain something. There's a difference between heat capacity. Remember, there's something called specific heat capacity, right? Specific heat capacity, we usually write SHC. Now, the truth is, the real symbol for specific heat capacity is a common C. Remember, write common here. The reason I'm specifying it's common, right, is that there's another value called heat capacity. Heat capacity does not have the word specific in it. let me explain what the difference between specific heat capacity and heat capacity is. Remember this formula: to calculate heat energy, it's mass by specific heat capacity multiplied by the change in temperature. The triangle T means change in temperature. What do I need to put here? Common C or capital C? Well, what's the real symbol for specific heat capacity? Common C or capital C? Common C, right? So when you're writing it, make sure and write it small, right, in the exam, right? So if it's the specific heat capacity of water, you can put C and a W. If it's the specific heat capacity of ice, you can put common C and a little I for the examiner, so you know what specific heat capacity you are referring to. So what is heat capacity? The capital C. Well, here's the slight difference. Anytime you take mass and multiply it by specific heat capacity, you get heat capacity. So the formula for heat capacity is mass multiplied by specific heat capacity. I have the formula down here for you guys because this is a real popular question in the exam. Specific heat capacity deals with 1 kilogram. So if I tell you the specific heat capacity of water is 4,200, I am talking about 1 kilogram of water. So whenever you hear the word specific, they're always talking about 1 kilogram of the substance. Heat capacity, which is very useless, this is my personal opinion, the mass is not known. So if I come and tell you the heat capacity of a strange metal is 24, you don't know how much mass of the metal I am talking about. You don't know whether it's 2 kilograms of the substance, 1,000,000 grams of the substance. But if I tell you the specific heat capacity of the substance is 24, you know I am referring to 1 kilogram of the substance. Right? So here are the definitions I need you to learn off for the exam. The first one is for heat capacity. It's basically what I just said. The units are different for heat capacity. It's joules per degree Celsius or joules per Kelvin. Specific heat capacity, it's joules per kilogram degree Celsius. It has a kilogram squeezed in here for both of them. Take down all the definitions, everything on the screen here, and learn it off by heart for the exam. The definitions are worth, well, these definitions are worth 2 marks in the exam. And know your difference between the capital C and the common C. Right? So take that 2 minutes and let me know when you are finished. So just for recording purposes, I made some mistakes here. This word was supposed to be is, and this word also is. All right, so let's move on to the next slide. Right. So now is the definitions of specific latent heat of fusion, right? Remember, the latent is the one where there's no change in temperature, just a change in state. Fusion is the one that involves solid to liquid or liquid to solid. In other words, they only involve solids and liquids. I have it written here. And the vaporization latent heat, once again, has nothing to do with change in temperature, only change in state. But this one deals with liquids and gases, like a liquid turn into a gas or the gas changing back to the liquid. All right, so these are the 2 definitions. You get roughly, well, these definitions, you might get at least 2 marks for each one of them in the exam. So I don't think you need too much time to take this one down, but a minute and a half, and we will move on. Right. So how much of you all have done this in school already? Usually, well, you just do this in integrated science as well, like in Form 3 and Form 2. The difference between a clinical thermometer, we all know thermometers are used to measure what? Temperature. However, clinical thermometers are used by doctors. And the main difference, the laboratory thermometer are used in labs, like when you go in the school lab and things to do experiments and whatnot, you use a laboratory, how you call it? Thermometer. I made a small mistake here, right? For the laboratory thermometer, it goes from minus 10 degrees. I write the minus sign here, so it was kind of hard to see, okay? It goes from minus 10 degrees to 110 degrees. So the thermometer can actually measure things colder than 0 degrees ice. It can be used to measure really, well, not really cold temperatures, but cold-ish temperatures. And it goes all the way up to 110 degrees degrees Celsius. But you see, a doctor, well, when a doctor is measuring the temperature of a patient, right? It only goes from 35 to 42. A doctor does not need a laboratory thermometer because if a person is at 0 degrees Celsius, they're dead, right? And if a person body temperature is 110 degrees, they're dead, right? So doctors only need temperatures to be measured from 35 to 42. By now, everyone knows 42 is a really high body temperature. And that's basically, is probably, if you go and you measure your temperature and it's 42 degrees, there's a good chance you're not going to make it. All right. So these here are the little differences between a clinical thermometer and a laboratory thermometer. The clinical thermometer has a little constriction here. So after you take the temperature remains, the mercury remains at the same height. In a laboratory thermometer, when you remove the thermometer from the liquid or whatever you are measuring, it begins to drop, right? So I think any notes here are pretty self-explanatory. I don't want to bore you all too much. Do me a favor, take down everything on the screen here, right? There's no need to draw the diagram, so just the table. Right. The kink is the same thing as the constriction here, right? So K-I-N-K. Right. Now, if you all notice, both thermometers cannot really measure extreme temperatures. Like, for example, the clinical thermometer can only measure between 35 and 42 degrees. The other thermometer, the laboratory thermometer, I mean, it goes down to minus 10 degrees and goes all the way up to 110. But that's not extreme temperatures. Suppose it have something really, really cool, like at a minus 170 degrees Celsius, or you have a real hot piece of metal, like 350 degrees Celsius. You can't use either of these thermometers to measure those extreme temperatures. Also, think about it like this. When a doctor is measuring your temperature, like he will usually put the thermometer underneath your arm. He will leave it there for about a minute. The reason he leaves it there for a minute is because these thermometers, even this thermometer, right, takes a little while to rise. The mercury inside the thermometers do not react immediately. Even though the laboratory thermometers are a little bit faster, in my opinion, it's still slow to measure what temperature. You have to at least leave it inside the liquid for, I don't know, about 10 seconds or 30 seconds to at least get the accurate reading. Also, if there were two pieces of metal, let me say there were two pieces of metal, one on top each other, and there was a small opening in between these two metals. You see the little crease here? How are you going to push this or this, which is made up of glass, in between two pieces of metal to measure the temperature in between two pieces of metal, right? All right. So it's going to be a little bit difficult in a case like that. So there, if you want to do extreme things like that, you need a different type of thermometer. The other type of thermometer that can deal with these extreme cases is something called a thermocouple. Now, a thermocouple is a real simple device. Well, when it was first made, it was a very, very simple device, but now it has some really, really accurate thermocouples. A thermocouple, believe it or not, is just made up of two different materials of metal. It's a really simple device in theory. For example, this thermocouple is made up of copper. That's one type of metal. And the other type of metal is iron. You will see it here. Now, whenever you dip one end into a substance, like something hotter, and the other end into something cold, naturally, it is form a current. And this current, depending on the temperature, will produce a different current. Okay? And that current can be converted into representing a temperature. It's a real simple device. I actually first learned about a thermocouple when I was a small boy, when I was watching this cartoon called Ghostbusters. It was a cartoon long time. And they ran out of electricity. So the smart guy in what's his name in Ghostbusters, the one with the glasses, he built something called a thermocouple to create electricity. And a thermocouple, like I said, it's just a very simple device. It's made up of two different metals joined together. And when one end is put into a hot place and the other end is put into a cold place, it naturally generates a current. And the larger the current means the larger the temperature difference. All right. But to keep things simple, right? In the exam, they could ask you to draw a thermocouple. I've seen this come. This is actually the answer for a past paper question. They could ask you to draw a thermocouple. So this is one way you could draw it. This is another way you can draw it. They will ask you, what is a thermocouple? And what are the advantages of a thermocouple? I believe everything on the screen is self-explanatory. Would 5 minutes be enough for this, for you guys to take it down, to draw and take down?